Yeah, spring force we have done, Tej. I have explained to you spring force earlier. Okay. The concept of spring force has been covered in the last to last lecture. Okay. So there's nothing more to it really. So you can just work out the questions from H.C. Verma with it. And then when we are doing the doubts of friction and Newton's laws collectively, we will pick up some more questions. Okay. Let us continue with the topic ahead right now. Okay. Right, so this is friction session number 2. So quick recap of what we learned about friction last time. So what we understood is that friction is a type of contact force, okay, that acts tangentially. That means parallel to the surface of contact. Okay. Such that it either prevents slipping by balancing the external tangential force. In that case, it is called static friction. Okay. And we have the property that static friction can be anything from 0 up to a maximum value of coefficient of static friction into normal reaction. So this is called the limiting friction, or the maximum limit of static friction. Or it can be acting in such a way that it is opposing slipping. Okay. So in this case, it acts while there is slipping. But against the direction of slipping. So when this kind of situation happens, as you know, it is called kinetic friction. Okay. And kinetic friction has a fixed value of mu k into normal reaction, where mu k is the coefficient of kinetic friction. Okay. So just make sure you understand this quick recap of this. Then we will look at some more examples of the application of the same thing. No, buoyant force is a completely different category of force. Yes, we will discuss about buoyant force in something called fluid mechanics. And friction by the air or air resistance is also a different type of force. It is called viscous force or viscosity. So it is different than friction. Okay. Friction over here is the contact force between two solid surfaces. Okay. So air is basically a fluid. Okay. Fluids include the category of liquids and gases. So forces because of fluids comes in a different category in fluid mechanics. It does not come in the category of contact forces. Okay. But yes, in it has similar property in the sense that air resistance also opposes the relative motion, or it opposes the motion of a body inside in air. Okay. Whereas buoyancy does not do that. Buoyancy is completely different. It always acts upwards against gravity, opposite to gravity. Okay, so let's pick up an example again to make sure that we understand the concept of kinetic and static friction and also the numerical application of coefficient of friction. So similar situation to the basics that we had seen last time when we were looking at the definition of coefficient of static friction and kinetic friction. So we have this rough surface on which this body is initially at rest, and this surface has a given coefficient of static friction as 0.5 and a given coefficient of kinetic friction as 0.4. So many times you will see in numerical problems two separate coefficients are given. That means these static and kinetic friction have distinct values in their coefficient, and always the coefficient of kinetic friction will be less than the coefficient of static friction. On the other hand, in certain questions, you will see that there is only one coefficient of friction given, like mu is equal to something 0.4. So when something like this is happening in a question, what you have to assume is that the coefficient of static friction is exactly equal to the coefficient of kinetic friction, and that is 0.4. Okay. So two separate kind of situations you will have, one where separate or distinct values of static and kinetic friction's coefficient are given, and the other where a single value of coefficient of friction is given, and in that you will have to assume that the two values are the same. Okay, right. So this is given, and the mass of the object is, let us say, 5 kilograms, and the acceleration due to gravity is 10 meters per second square. Okay. Now a constant horizontal force is applied. F is applied from t equal to 0 onwards. Okay, such that, so let's say we start applying this external horizontal force. From this side we start pushing it, such that the magnitude of this force is equal to 40 newtons from t equal to 0 to t equal to 10 seconds. Okay, then the force is increased to 60 newtons from t equal to 10 to t equal to 20 seconds. Okay, and then F stops acting, so that force is withdrawn after t equal to 20 seconds. So first of all, find the frictional force and acceleration or deceleration of the block in each of these situations. And second, plot the velocity time graph for this block. So for each of these parts, you have to find out the amount of friction acting and the amount of acceleration or deceleration the block will have. So obviously for the first part, you can make free body diagram to understand this better. Okay. So just try this out, work out this question. We will discuss the solution soon. So make the free body diagrams for each of the parts A, B, C, and work out the magnitude of friction and acceleration or deceleration, and send me the answers over the text message, please. Yes, Vashist, your answer is correct. Yes, you have to check your solution. So I will just start by giving you a hint that no matter whether you are applying external force or not, the weight balances normal reaction. So normal reaction is equal to mg equal to 50 newtons. Okay. So maximum friction for the static case is going to be 20 newtons. Sorry, is going to be 25 newtons. Okay. Whereas kinetic friction is going to be 20 newtons. So what is going to happen here is if the external force is more than 25 newtons, the block will have to accelerate. And once it accelerates, the friction acting will be 20 newtons, okay, because it will be kinetic friction. Okay. So Diti, you're giving the answer for the second part or the first part? So anyway, the answer for the first part will be No, unfortunately, that's not correct. But answer for the first part will be that the friction acting on the block in A part, the friction acting will be kinetic friction of 20 newtons. Okay, and the acceleration of the block will be 4 meters per second square. Whereas when we increase the external force to 60 newtons, the kinetic friction will remain 20 newtons, but the acceleration would increase to 8 meters per second square. Now think what will happen in the C part also. Yes, Vash is very good. That's correct. Okay, so let us understand each of these parts. So first of all, we can see that normal reaction is equal to mg. Okay, so that is why in the first part, for F equal to 40 newtons, F is greater than maximum friction. Okay, so that means the block starts to slip, and kinetic friction of 20 newtons acts on it. So the free body diagram looks like this. So by substituting the values, you get the acceleration as 4 meters per second square, and the friction (20 newtons). Okay. Also, what happens is that because of this acceleration, this is from t equal to 0 to t equal to 10 seconds. So initially, the velocity was 0. So velocity becomes a function of time like this. So by the time you come to 10 seconds, the velocity at 10 seconds becomes 40 meters per second. Okay, so this is what is happening initially. So you can also keep track of the velocity versus time graph. This is what is happening initially. Now next up, for F equal to 60 newtons from 10 to 20 seconds, again your FBD is much the same. There's no difference really, but the value of acceleration changes. So let's say this acceleration is A prime. So now A prime becomes the new value of force, okay, which is 60 newtons minus the same value of kinetic friction, that doesn't change, divided by the mass. So it has an acceleration of 8 meters per second square from t equal to 10 seconds when the velocity was 40 meters per second to t equal to 20 seconds. At that point of time, the velocity will become how much? It will become 40 plus 80, so 120 meters per second. So now the second part of the journey, you can see that the velocity had increased to 40 in 10 seconds. Now it will increase this way. To 120 in the next 10 seconds. Okay, so this is what is happening in the first two parts. Now you see what's happening after 20 seconds. You withdraw the external force, but the block is already slipping. So it's in a state of slipping. So kinetic friction acts to oppose the slipping. That's why there will be deceleration in the third part. Okay, now let's come to the third part and understand what's happening here. So from t equal to 20 seconds onwards, the force is withdrawn. But remember, the block is moving or it is slipping already because you are applying force. So at t equal to 20 seconds, it is in a situation where it is moving with a velocity of 120 meters per second. Okay. So because it is slipping, kinetic friction will act opposing it. Okay. So because it is moving or slipping, kinetic friction acts opposing the slipping. Okay. So there is deceleration. So it decelerates the block until it stops. So eventually it will stop at some point of time. So it will create some deceleration, let's say a double prime. ठीक है. और उसके वजह से eventually at some instant of time, you don't know, but the velocity will become zero. So the moment the velocity becomes zero, now friction stops acting because no longer slipping is occurring. Okay. So for this free body diagram, we can see that kinetic friction is equal to m into a double prime, where a double prime will be the deceleration from t equal to 20 until the block stops. Okay. So you can see that this will be, so from that we can see that the deceleration will be 4 meters per second square. Okay. So since velocity at 20 was 120 meters per second, okay, so velocity will become zero after delta t equal to 120 by 4 or 30 seconds. So eventually the block will stop at 30 seconds. Okay. So from this data, now we will do the second part of the question. We will plot the velocity versus time graph. Understand that in detail. Okay, so let's understand the final part of the question. So to plot the velocity versus time graph from the beginning, remember, we are just so velocity in meters per second versus time in seconds. So the block started from rest at t equal to 0. And for the first 10 seconds, it had an acceleration of 4 meters per second square. So let's say its velocity increases like this. So it reaches a value of so this part, the acceleration was 4 meters per second square. So it reached a velocity of 40 meters per second at 10 seconds. Then thereafter that what happened? The acceleration increased because we increased the external force. The acceleration had increased to 88 meters per second square. Okay. So in the next 10 seconds, from 10 to 20, the acceleration was 8 meters per second square. So the velocity increased to 120 meters per second. But thereafter what happened? The block decelerated. So we stopped applying the external force. So thereafter it decelerated. It took about 30 seconds. So after a total time of 50 seconds, it is decelerating here. So we'll write it with a minus sign. Because external force had become 0. Whereas in these two parts, the external force was present. No? So it was accelerated motion. So this is the final graph of velocity versus time. Okay, so hope this question is clear to all of you. Next, we'll move on to problems where there are multiple blocks and things and there is friction involved. So for example, now if we have a situation like this, You have a combination of two blocks, okay, which are tied by a thread or something like that. And we start pulling this with some force F. Now this time just a single coefficient of friction is given to us, and it is 0.5. So the system was initially at rest. Okay, with these masses given, M1 is, let's say, 20 kilograms and M2 is 30 kilograms. And G is 10 meters per second square. Now, an external force F is applied. Find the acceleration of the blocks if any, that is, okay, and the tension in the string, the tension in the thread, if this external force is 100 newtons, 200 newtons, 300 newtons. So try this out, please. Make the free body diagrams of the blocks and try to understand what's happening over here. Okay, very good. That's correct. Vashisht, your answer about acceleration is correct. Okay, but tension will not be there in the first case. See, what you have to understand, na, ki when we are looking at the block M2 alone, look at the free body diagram of the block M2. Okay. Okay. So this normal reaction is 300 newtons and coefficient of friction is 0.5. Therefore, maximum static friction on M2 is 150 newtons. Okay. So therefore, from this, what we can understand that if F is less than 150 newtons, less than equal to 150 newtons, then static friction will balance F and tension will be 0. Okay. And only if F is greater than 150 newtons, okay, then tension will be non-zero. Okay. And then there might be two cases. Okay. Tension might be non-zero such that acceleration is still 0 because friction on M1 is able to prevent slipping. Okay. Or acceleration is non-zero because friction is unable to prevent slipping. So these two different situations are possible. Okay. So let's understand them in terms of free body diagram also. So here if I assume that F is less than 150 newtons, less than equal to 150 newtons, then यहाँ पे static friction balances F, tension is 0, acceleration is 0. So the second block in fact has a free body diagram which now looks like this. M1, on M1 there is no tension acting only. Okay, so there is only normal reaction and weight acting on it. Okay, this is the case. So this is what will happen in the first part. F is equal to 100 newtons only. So that means static friction on M2 balances F. Okay, tension in the thread is 0 and acceleration is 0. Yes, that's correct, Yash. For the second part is correct. Okay, so now based on this, you work out what happens in this situation next. Okay, so from that you'll understand what's happening in second and third part. Excuse me. Yeah, now see, second part, you increase the force to 200 newtons. Okay, so therefore, the force is greater than the maximum static friction on block M2. Okay, so therefore, M2 has a tendency to slip. Okay, so therefore, it pulls on the string. So tension becomes non-zero. Now we want to check that does M1 have enough friction available to prevent slipping. That is the thing we have to check now. Okay, so come back to this free body diagram. But now you understand this pair of free body diagrams. But now we understand that there is a tendency to slip. Okay, for the block M2. So maximum friction will act on it. Okay, but that will not be enough to prevent slipping. Okay, so now that means there will be some tension acting. Okay. Now assuming no slipping, okay, इस पे क्या act कर रहा होगा? Maximum static friction. So that is mu n2. Okay, or इस पे there will be some amount of static friction acting, which we don't know. Okay, but we know that the maximum static friction on M1 is mu n1. So that is 0.5 into M1G. So that is how much now? That is 100 newtons. Okay. So we assume the acceleration is 0. Therefore, for A to be 0, that is no slipping. Okay, this tension should be less than equal to mu n1, or tension should be less than equal to 100 newton. Tension should not exceed 100 newtons. Okay, so now let's see what is happening in this case when the force we apply. So in the B part, the force we apply is 200 newtons. Okay, so therefore tension will be F minus mu n2, assuming acceleration to be 0. Okay, so the tension will be 50 newtons. So we can see that yes, acceleration will be 0, and friction on M1 will be equal to 50 newtons, which is less than mu n1. So the conclusion will be for the B part, acceleration will be 0, tension will be 50 newtons, and friction of mu n2 equal to 150 newtons acts on M2, and friction of 50 newtons is less than mu n1 acts on the block M1. So this is the final result of the second part. Okay, now similarly work out the third part, please. This will give you a good idea about how to analyze the third part, where the force is increased to 300 newtons. Capital F is 300 newtons in the third part. So if you've written this down and understood this part, please start working on that. Okay, yes, let me verify. Yes, the acceleration is correct. Very good. So third part, you should be getting an acceleration of 1 meter per second square. Okay, and the tension will become, wait, I'll just tell you the tension. (120 newtons), that's correct. Okay, and kinetic friction of 150 newtons acts on M2, and kinetic friction of 100 newtons acts on M1. Okay, so again you can see that in this part, when you increase the force to 300 newtons, the external force is 300 newtons. Okay, so if you assume no slipping, okay, then on this block you will have to assume that, okay, the maximum static friction of mu m2g, which is 150 newton acts. Okay, so you'll have to assume that the tension balances the rest now. So tension will become F minus this maximum static friction, so it will be 150 newtons. Now this is the required tension. Now you can see that as far as M1 is concerned, if the tension is as much as 150 newtons, then here we don't have enough friction, because this has a maximum value of mu m1g, which is 100 newtons. So you can see that this is not possible. Okay, so this tension of 150 newtons, this cannot be balanced by static friction on m1. Okay, therefore slipping will occur, and once we know slipping occurs, we know that kinetic friction will act on each block. Okay, so on m1 there will be kinetic friction of mu m1g of 100 newtons. On m2 there will be kinetic friction of mu m2g of 150 newtons. Okay, and they will have common acceleration. So you know this information. So now we have to adjust our free body diagram according to this. So first of all, we know that both of them will have common acceleration. Both of them will have kinetic friction. Okay. And there is some tension like this. Okay. So according to this, now we understand that for this we will have the equation mu f minus t minus mu m2g is equal to m2a. So that is 300 minus t minus 150 is equal to 30a. This is our equation 1. And for this one, we have the equation t minus mu m1g is equal to m1a. So we have t minus 100 is equal to 20a. That's our second equation. So now you can just add these two equations. Okay, so that becomes the final solution. Okay, so this is an important question to understand the working of kinetic and static friction in different situations when we have a system of blocks instead of a single block. So please note this down carefully. Make sure you understand the third part in particular. All right, people. So hope this example was clear. As I told you, a very critical example to understand the working of friction in a situation where we have a system of blocks. Okay. Now we'll come back to system of blocks and these things again. But before that, let's take another look at something very important: friction on an inclined plane. Okay, so we will look at now the situation of a rough inclined surface. So we will develop a critical or an important formula over here for basically the critical condition of whether or not an object can remain at rest on the inclined plane because of the friction available. So if this has a coefficient of static friction mu s and a coefficient of kinetic friction mu k, okay, let us understand the condition for the object to remain at rest. So we will develop now the condition for a block or any object of mass m to remain at rest in equilibrium, that is when placed on the surface versus the condition for it to slip down the inclined plane. So let's understand that by looking at the free body diagram, the block. So the forces acting on the block we know are the weight, the normal reaction, some kind of friction. We know here that this angle is theta, this angle is theta. So when we look at the detailed free body diagram with the components, we can see that mg's components are mg sine theta down the incline and mg cos theta into the inclined surface. And normal reaction balances mg cos theta, whereas the friction is the one which is trying to prevent slipping. So it will act opposite to the tangential force which is giving a tendency to slip. So this will be friction in general. Now we'll talk about when it is kinetic and when it is static and all that. But before that, let us understand this free body diagram in full detail here. So if you see with respect to the vertical and horizontal, this angle was theta here, this angle is theta, this theta. So here we can understand that mg sine theta, this is the component of weight which is trying to make the block slip. Okay, this is the component of mg which is tangential to the surface. And tends to make the block slip. Okay, and therefore friction acts against against it. Okay. So now the condition for friction to be successful, we will understand from the maximum static friction available. वो कितना हुआ? That will depend on the coefficient of static friction. So this friction's maximum possible value is mu s into normal reaction. Now we can also see that normal reaction is equal to mg cos theta. So we have this already. Okay, from this diagram you can see this. Okay. So the maximum static friction available to us is mu s into mg cos theta. Okay. So therefore, if this is greater than or equal to mg sin theta, okay, then the block will not slip. That is the condition for the block to not slip. Okay. So basically, mu s into mg cos theta should be greater than equal to mg sin theta. Or in other words, the coefficient of static friction should be greater than equal to tan theta. If you just take the cos theta on that side, this is the condition for no slipping. Okay, so I told you that there's a condition between the inclined surface, that is the angle theta, and the coefficient of friction available. So this is the condition. So this is the condition for the body to remain at equilibrium. Okay, or what we can call the no slipping condition. Okay, so this is an important formula that we will keep in mind from this point onwards. Okay, in the analysis of friction on an inclined plane. So just go through this part. We will discuss in detail about its application with some examples also. Okay, now from this, people, we can also understand what is the situation if this critical condition is not satisfied. Okay, so if mus, so in this case, if mus is greater than tan theta, then the block does not slip. Okay, that is obvious. Okay, and what happens? The static friction balances mg sine theta. because the acceleration is 0. That you can see from the FBD above. Okay, static friction will balance mg sin theta. Okay, so in this FBD, what will actually be happening is that the friction will be static in nature. Just a moment. Yeah, so in this free body diagram, this friction will be static in nature and it will be balancing the mg sin theta component. Because the acceleration will be 0. Okay, this is the situation where mu s is greater than equal to tan theta. So when this happens, the static friction will be equal to mg sin theta and acceleration will be 0. This thing. Okay. Now on the other hand, let's understand what happens on the other hand if the static friction is not able to prevent slipping. So if the coefficient of static friction is less than tan theta, okay, that means mu s into n is becoming less than mg sin theta. Okay. So in that case, static friction cannot prevent slipping. Okay. So in that case, the situation will become like this. The friction acting now will become kinetic friction. And the block will start to accelerate down the inclined plane. So because friction cannot prevent slipping, so the block slips with a non-zero acceleration. Okay, and kinetic friction of mu k n, that is mu k into mg cos theta, acts. So now you can see down the inclined plane, your equation will become mg sin theta minus kinetic friction is equal to mass into acceleration. So this becomes the equation. Okay. And now you substitute this value here of kinetic friction. So this becomes mg sin theta minus coefficient of kinetic friction into the normal reaction, which is mg cos theta. That becomes equal to the net force. So it's mass into acceleration. So from this equation, we get the magnitude of the acceleration. It becomes g into sin theta minus coefficient of kinetic friction into cos theta. So this is the acceleration of the block. Okay. Okay, so this is the acceleration when this is less than tan theta. So slipping is taking place. Okay. Whereas when coefficient of static friction was greater than equal to tan theta, then the acceleration would have been 0 and the condition would have been static friction balances mg sin theta. Okay, so let's just understand with an example or two. So for example, suppose we have an inclined plane which has an angle of inclination of 30 degrees, okay, and a block of mass 2 kg is placed. It is given to us that the coefficient of static friction is 0.7 and the coefficient of kinetic friction is 0.65. So we have to find the acceleration, if any, okay, and the friction, okay, whether it is static or kinetic, that is acting on the block. Okay, take G as 10 meters per second square. So first thing we will do here is that we will check the condition for slipping versus no slipping. So for that, what we have to check? For slipping, coefficient of static friction should be less than tan theta. Whereas for no slipping condition, coefficient of static friction should be greater than tan theta. So here you can see that tan theta is tan 30 degrees, which is 1 by root 3, which I can write as root 3 by 3 or approximately, okay, so something like this, okay. Whereas coefficient of static friction given to us is 0.7. So you can definitely see that coefficient of static friction is greater than tan theta. So which condition it will satisfy? It will satisfy this condition. So therefore, acceleration will be 0. Okay. And now your free body diagram will very simply show you that on the block, okay. So mg sine theta will be balanced by static friction. So static friction here will become 2 into 10 into sine 30. Okay. So 10 newtons of static friction acts. Whereas you can also check that maximum static friction which is available, which is mu s into normal reaction, is 0.7 into mg cos theta. So it is 0.7 into 20 into root 3 by 2. If we check this value, you will see this is quite a bit greater than 10 newtons. This will be 0.7 into 1.73 into 10. This is 11 point something. So you can see that it's greater than 11 newtons even, the maximum friction. Whereas how much is needed? Only 10 newtons. So only this much static friction will act and acceleration of the block will be 0. Okay, so hope the application in this question is clear. Okay, now work out a similar question yourself. Next example. So in this situation, suppose the angle of inclination this time is 37 degrees and a single coefficient of friction is given to us of mu equal to 0.5 and a block of mass 5 kg is placed on the surface. So again, find out acceleration and friction acting on it. Take g as 10 meters per second square. The mass of the block is 5 kg. Okay, just take down the data of this question, then I'll take you back to the previous question. Okay, so I'm just taking you back to the previous question solution once, but in the meantime, if you finish this, you can start with the new one. Yes, Vashish, that's correct. Very good. Okay, so now in this case, you can see that first of all, that only a single coefficient of friction is given to us. So we have to take the value of mu s equal to mu k equal to 0.5. Okay. Second, you can see that tan theta, which is tan 37 degrees or 3 by 4 is 0.75. So in this case, we can see that mu is less than tan theta. So it is the condition for slipping. So slipping occurs here. So in this situation, what will happen is that the block will be accelerating down. Because of this kind of situation. So these will be the forces. So you can see that down the inclined plane, the net force will become mg sine theta minus kinetic friction. That's your main equation. Whereas normal reaction balances mg cos theta. We'll substitute this here. So there will be an acceleration of 2 meters per second square. Whereas you can see the friction acting will be kinetic friction equal to mu mg cos theta. So that is 0.5 into 50 into 4 by 5. So 20 newtons of kinetic friction is acting. Okay, people. So hope this question is clear. So with that, we conclude today's session. So I will send you the recording and the notes of both the last session and today's session. So please go through the basics of friction very carefully before your major test 4. Also prepare the trickier type of problems in Newton's laws of motion, like the constraint relation type of problems, multiple pulley systems, and pseudo force application in non-inertial frame very carefully for the test coming up, because the level of questions will be of the proper JE level for Newton's laws of motion. Whereas for friction, you can just rely on the examples we've done in class, the basic type of examples of single block systems having friction. And you can start with few questions from H.C. Verma's friction chapter also. But basically, as long as you're clear with the concept of static and kinetic friction and the coefficient of friction, limiting friction condition, etc., should not have too much difficulty with friction. So that's it for today's session, people. Wish you all the best.